Our next illustrated example problem features a voltage source of unknown magnitude supplying power to three series resistors. R1 having a value of 470 ohms, R2 has an unknown value, and R3 has a value of 300 ohms. We additionally know that R2 is experiencing a 5.2 volt drop, and the total resistance seen by this source is 900 ohms. We're being asked to solve for the voltage drop across each element, the current through each element, the power dissipated by each element, the supply voltage, the source current, total power, and the unknown resistance R2. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Again, before we begin this analysis of the circuit, it's perhaps worth a moment of our time to review fundamental series circuit properties. Current through elements in series is the same. This is the most fundamental series circuit property. For this series circuit, I source equals I1, which equals I2, which equals I3. If we solve for current through any element, we by extension also solve for current through all remaining elements. Kirchhoff's voltage law states that for any closed loop, the summation of voltage rises equals the summation of voltage drops. A Kirchhoff's voltage law analysis of this series circuit suggests that E equals V1 plus V2 plus V3. Power in always equals power out. For this circuit, power in equals P1 plus P2 plus P3. Finally, series resistances add up. For this circuit, total resistance is equal to R1 plus R2 plus R3. An algebraic rearrangement of the total resistance formula, solving for unknown resistance R2, demonstrates R2 to be the remaining 130 ohms. R2 is now a known resistor experiencing a known voltage drop. An application of Ohm's law solving for I2 demonstrates I2 to be 40 milliamperes. Current through elements in series is the same. I source equals I1, which equals I2, which equals I3, and they all equal 40 milliamperes. An application of Ohm's law solving for V1 demonstrates V1 to be 18.8 volts. Yet another application of Ohm's law solving for V3 demonstrates V3 to be 12 volts. Substituting in our calculated voltage drops into the Kirchhoff's voltage law equation demonstrates that the supply voltage must induce a 36 volt rise. As a means of checking our work, an application of Ohm's law solving for supply voltage demonstrates that source current times total resistance does indeed yield 36 volts. All we need to do now is use these known voltage and current figures to solve for power. Power is equal to voltage times current. P1 equals V1 times I1. Substituting our given values demonstrates R1 is dissipating 752 milliwatts of power. Power is also equal to voltage squared divided by resistance. P2 equals V2 squared divided by R2. Substituting our given values demonstrates R2 is dissipating 208 milliwatts of power. Power is also equal to current squared times resistance. P3 equals I3 squared times R3. Substituting our given values demonstrates R3 is dissipating 480 milliwatts of power. Power in equals power out. The summation of P1, P2, and P3 demonstrates the source must be providing 1,440 milliwatts, or approximately 1.4 watts of power. As a means of checking our work, supply voltage times source current does indeed yield 1,440 milliwatts of power. I've got a reasonable degree of confidence these answers are correct. We can move on to the next illustrated example. Our next illustrated example problem features a 48 volt source in series with three resistors, R1 having a value of 200 ohms, an unknown resistor R2, and R3 having a value of 300 ohms. Additionally, it is known that resistor 2 experiences a 16 volt drop with a given polarity. We're being asked to solve for the voltage drop across and the current through each element. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Again, before we begin the analysis of this circuit, it's perhaps worth a moment of our time to review fundamental series circuit properties. First, current through elements in series is the same. This is the most fundamental series circuit property. For this series circuit, I source equals I1, which equals I2, which equals I3. If we solve for current through any element, we by extension solve for current through all remaining elements. Additionally, Kirchhoff's voltage law states that for any closed loop, the summation of voltage rises equals the summation of voltage drops. A Kirchhoff's voltage law analysis of this series circuit suggests that E equals V1 plus V2 plus V3. Where to begin? Since we've been given some known voltage values, it's perhaps easiest to begin with Kirchhoff's voltage law. An algebraic rearrangement of the Kirchhoff's voltage law equation, solving for the unknown voltages V1 and V3, suggests that V1 plus V3 equals 32 volts. How would 32 volts be apportioned between these two known resistors? We can utilize a simplification where 32 volts is across a 200 ohm resistor in series with a 300 ohm resistor. This is a perfect setup for the voltage divider rule, which states the voltage across the element of interest, Vx, is equal to the resistance of the element of interest divided by the total resistance for that series path times the voltage across that series path. Using this simplified circuit, the voltage divider rule set up for V1 is equal to V1 divided by R1 times R1 plus R3 times the total voltage across this series path of 32 volts. Substituting in our given values demonstrates that V1 is 12.8 volts. An application of Ohm's law solving for I1 demonstrates that I1 is 64 milliamperes. Current through elements in series is the same. I source equals I1, which equals I2, which equals I3, and they all equal 64 milliamperes. An algebraic manipulation of the Kirchhoff's voltage law equation for the simplified circuit of R1 in series with R3 demonstrates V3 to be the remaining 19.2 volts. As a means of checking our work, an application of Ohm's law solving for V3 similarly demonstrates that V3 to be the remaining 19.2 volts. The voltage across and the current through all elements has been solved for. All that remains is solving for unknown resistance R2. An application of Ohm's law solving for R2 demonstrates R2 to be 250 ohms. Alright, one more example problem remaining. Alright, our last illustrated example problem features E1, an 8-volt source, in a series aiding relationship with E2, a 6-volt source, and a series combination of 3 resistors, R1 having a value of 300 ohms, and R2 and R3 are unknown resistors. R2 is experiencing a 2-volt drop with a given polarity, and R3 is experiencing a 3-volt drop with the indicated polarity. We're being asked to solve for the voltage drop across each element and the current through each element. And just to make it challenging, we're additionally being asked to solve for unknown voltage Vx with the indicated polarity. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Let's dive right into a Kirchhoff's voltage law analysis of this circuit. A Kirchhoff's voltage law analysis of this loop suggests that E1 plus E2 equals V1 plus V2 plus V3. We have 2 known voltage rises, 2 known voltage drops, and 1 unknown voltage drop V1. An algebraic manipulation of the Kirchhoff's voltage law equation solving for unknown voltage V1 demonstrates V1 to be the remaining 9 volts, where polarity is assumed positive to negative left to right. An application of Ohm's law demonstrates I1 to be 30 milliamperes. Current through elements in series is the same. This is the most fundamental of series circuit properties. Source current equals I1, which equals I2, which equals I3, and they all equal 30 milliamperes. Given known voltage and known current, we can solve for unknown resistance R2. An application of Ohm's law demonstrates R2 to be 66.7 ohms. Similarly, an application of Ohm's law solving for R3 demonstrates R3 to be 100 ohms. Now we need to solve for unknown voltage Vx with a given polarity. There's a couple ways of doing it. A Kirchhoff's voltage law analysis of this loop, traveling in the clockwise direction, demonstrates that rise E1 is equal to the summation of voltage drop Vx plus voltage drop V3. Substituting in our given values demonstrates that Vx is 5 volts. Other loops yield similar results. For example, this loop in the clockwise direction demonstrates that rise Vx plus rise E2 is equal to the summation of voltage drop V1 plus voltage drop V2. Substituting in our given values similarly demonstrates that Vx is 5 volts. I've got a reasonable degree of confidence our answers are correct, and we can bring this lecture to a close. In conclusion, this lecture examines several illustrated examples of series DC circuit analysis featuring circuits with unknown values. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.